Hello, I'd like to welcome you to the training video for the Newfangled Wizards add-ons for Mach3 Mill. To enter the wizards, we're going to press the conversational button. The term conversational programming is kind of one of those things where it's a little generic, but basically it's the ability to make a G-code program at the machine. So we kind of think we're fitting that at this time. The first screen that we're brought to is the material selection screen. On the material selection screen, basically we're picking the materials that we're going to be machining. We do have a limited selection of materials, like the ones that you're seeing on your screen right now. If we encounter materials that are not on the screen, just pick something that's kind of similar. For example, if I was going to cut some wood, I would probably select aluminum. If I was going to cut stainless steel, I might select steel, medium, or hard, depending on whether I was doing like 304 or 316 stainless. For our example, we're going to go with steel, soft. On this side, we have machine data, maximum spindle speed. This is the speed at which we never want our spindle to be programmed to go beyond. It's a capped limit that when the calculations are done, if speed is determined to be faster than that, it will not exceed. And the same with max feed rate. And we have our units. Units is going to put a G20 or a G21 at the beginning of our program. This LED will get set when you enter into the wizard by a script that's called, and it will set it to the native units of your computer. So if you have Mach3 set up in inches, it will automatically go to inches every time. So if you're going to do something that's in non-native units, you'll have to select this every time. Press the continue button. Now we're in the operations screen. We can see that there's many operations that we can do. There's a wide variety of operations, some of which will be added. We're going to be doing some stuff with patterns and whatnot, as it's been a popular request. But to get started, I think we'll select the circular pocket. We're brought to the tool properties page. This is where we're going to set up our tools initially. This one's kind of out of all the pages is probably the most difficult page for a new user, because you're basically trying to figure out everything you're going to do before you go set up your operation. Well, the first thing we're going to do is set our tool number. We're going to start off with tool 2, and we're going to run a diameter of about 1/2 inch. And the type of tool that we're going to run will highlight. Basically what we're doing is there's a big case statement inside of the Mach3 that's selecting which one am I going to use, and it assigns a surface speed to it. Well, what I mean by surface speed is it's feet per minute. So the feet per minute that are going by, or meters per minute if you're in metric, is if you were to wrap a string around your tool, and as it was running in 1 minute, how many feet or meters of string would it spool up on the cutter in 1 minute? So these are just generic values that were pulled out of a handbook. So we'll select high-speed steel, and if we hit the calculate, we can see what RPM it would like to go to. If I press carbide, I can see that it wants to go faster. With the tin-coated carbide, it wants to go yet again faster. But let's say I have a carbide tool that came and said that it needed to have 600 feet per minute for cutting speed. If I press the feet per minute in the calculate, I can see that I'm up to about 4,500 RPM, so quite a bit faster than a normal carbide tin-coated, which is only 2,670. The reason I put this is because some of the new tools run much faster than the old carbides and stuff, and I figured that a lot of the users would be more comfortable with this selection than trying to figure out what to put in this category. So that's just a little bit of history about why we put these in, and hopefully it makes a little more sense now. The number of cutting tips. This is just the number of tips on your end mill. And typically it will be 2, 3, or 4, but if you have a 6-fluted end mill, you're sure you can type it in. Ours would be 4 for this example. The chip load per tooth. The chip load per tooth is the cutting flute, and as it advances into a part, Every time it revolves, if we have 4 cutting flutes, it will take 4 chips every single time. So in one revolution, how far would it go? Would be the chip load per tooth times 4. So that's where the number comes from. But a typical amount would be anywhere from a 1/2 thousandths for a very small end mill, or up into maybe 8-10 thousandths for a fairly large end mill. The high feed carbide mills could be up into the 40s. That's why I didn't really set this, but this number is dependent on the diameter of the tool, the material you're cutting, and if it's set too low, you can rub a little too much and create too much heat locally to the tool, and it will burn out the tip. If it's programmed too high, you'll end up actually snapping off the bit or buying a new end mill. But in either case, it's not good for the tool, so a proper selection of this is very important. I would say for most of the machines that the hobbyist type market would be using would be maybe around 1/1000 to 1/2 thousandths to 2/1000. You're not going to get into any end mills that can take a real high tool load. You're also limited by motor horsepower. But motor horsepower should never be taken into consideration when setting your chip load per tooth. You should change your depth per pass. The chip load per tooth will affect cutter life. You could bury a cutter if it was strong enough, a foot deep in steel if you had enough horsepower and rigidity, but you never would want to take a really light pass if you had more horsepower to go deeper. So we'll leave this at about 2/1000. And we have our cutting direction. Typically this will be clockwise unless you get some left-handed tools. And we have flood and mist coolant. We can turn them both on, both off. It's up to you. Now we have overrides. Now let's say my high-speed steel end mill. I calculate the speed, and I'm fairly happy with that RPM, but if I wanted to be 10% faster all the time, I can type 110, and now my spindle RPM will be increased that 10% no matter what selection I have. This I will use a lot for finish passes, or if I have a machine that doesn't like the proper RPMs and whatnot. And the same thing for the feed rate. The feed rate, this one's very helpful for finish passes and whatnot, where you actually want to run a finer feed rate. So in roughing, I'll run 100%, and I might run 75 for finish pass, or if I have a lighter machine, maybe I'll run just a little bit less. Now we have our plunge feed rate. This is just the percentage of the traversing rate to plunge into the material when we get ready to go on a straight down feed. And as you can tell, this is where the RPMs and feed rate is calculated. If we wanted to, we could actually type into these DROs. If I just said I wanted to have 6 instead of that, if I hit continue, this will go into my program, and the same with the spindle RPM. So if you have a rate that you would like to program, you can just type it in here. Or if you want it to be calculated, just hit calculate speed and feed. Press continue, and cancel will bring you right back to the main menu. Okay, now we're brought to our circular pocket. We're going to do our first one about 0, 0. And this point is the center of this pocket relative to your G54 or 55 coordinate system that you have programmed. So this is going to be right at the 0 point of the program. Now we have the step over. Step over is kind of, well, it's the percent that's engaged of the tool during the cut. This number is more important than you might think because it actually controls the entry angle of the tool as we're cutting. If you want to think about it, anything greater than about a 50% is going to actually give you a negative entry angle because the inside of the cutting flute in here will hit before it does out here. That's a little bit, maybe not as important on the spiral fluted, but if you're running carbide inserts and stuff, that can be actually detrimental to the life of the insert. So if you're running carbide tooling and you find you're having some bad life, try and bump that down just a little bit, and you may actually get better life for your tool. We're going to bring this up to 75 for our first example. The pocket diameter we're going to leave at 1.9 inches, and that's just the diameter of the pocket we're going to cut. and we have the ramp distance. The ramp distance is actually how much it's going to pull off on its last move. If we were in metric, this would be way smaller than we'd really want. We'd want something quite a bit larger in maybe 2 to 3 millimeter range, but for inch this is a nice value. And if you're running a pocket and you see that your pocket in this 1/100,000th would actually crash into the other side, it actually won't. It will calculate it and truncate it before it's going to hit, depending on if you have a pocket diameter too small. The ramp angle will set to 0. We'll get to that in just a minute. We have a milling direction, just climbing conventional, a rapid distance, the step depth, and the total depth of the pocket. Now, if I hit preview, I can see I have a nice circular pocket. And this is the pull-off I was referring to earlier. And we can see that our downfeed is just a simple downfeed. This downfeed practice is actually fairly common, but for smaller, lighter machines, it's not preferred. If you had a smaller, lighter machine, you'd be much better off to actually helix into the part. That's why we added this DRO here. If we typed in, 3 degrees, try that again, for a carbide tool or even high-speed steel end mills, non-center cutting end mills can now cut blind pockets. They're a little bit cheaper, easier to regrind for the home type user, or indexable inserts because there's nothing in the center of the tool to actually cut with. If we hit preview, we can see that we now have a helix going right down the center of it. So it comes down to the surface of the part and comes down in a 3-degree helix. This is actually helpful because you can bump your feed rate way up and actually cut in relatively quickly without ever getting burrs and stuff pulling up as much. This works particularly well in wood. You could take a fairly soft wood, and by helixing down into it, the wood won't stick to the tool as much. And in metal, you can actually cut a little bit faster going down. The overall time to get down to the depth takes a little bit longer because you're taking a lot longer pass, but your machine, you won't even hear it plunging, whereas before you might see the spindle trying to move off to the side some. So that, we were pretty happy with that, but we really would like to have a little less step over. Now, as you can tell, I'm just hitting this until I look at the program and I'm like, wow, I really like that program. Or I say, geez, I really don't like it and I really would like some more step over. So we can just keep on playing with it until we see that we have a program that we really like. And I'm fairly happy with that one. We'll hit post code. As soon as we hit post code, it actually writes to the file that we're doing. In the other one, we were actually writing to a temp file. We're happy with our tool settings. We're going to do another pocket at 6 inches over. And we'll preview. And that looks nice. So this is in the temp one that we've written. Now when we press this one, we're actually going to write the code to the other code that we've produced. I'll show you that in the view toolpath. And we could cancel at any time. We hit verify toolpath. We can see we have 2 circular pockets, all programmed and ready to be cut. But we'd like to add some more features to it, like a finish pass on the wall. To do that, we'll use the cut circle wizard. Now, we're just going to use the same tool, but we really should bump our spindle speed up a little bit, and we're going to go about 120%. And we probably ought to bring our feed rate down just a little bit, maybe to 80%. Now we hit the post code, we can see that, the calculate speeds and feeds. We can see that our RPM has come up and our feed rate changed a little bit. Continue. Now, since we had just done our last hole over the 6-0 position, I'm going to bring this one out to 6. That'll cut down on our rapid time. That's fine. And we're going to cut a 2-inch diameter pocket. Now, this groove command, what this does is it stops your entry moves from happening inside the part. So if I actually wanted to cut this groove right here, I could use this groove command. It would do its compensation move above, drop down, and then cut the part. So I could have an oil ring groove or anything like that if I was building a small steam engine or just needed a circle to be cut out in a part. and we don't need that. Then at any point you can say which side of the circle I'd like to be cutting on. We're going to cut on the inside, and then we can do climb milling or conventional milling. We'll keep on doing climb milling. And we're going to set our pitch to 0 initially. And we have a rapid height of 0.1, a step depth of 0.125, and a depth of 0.75. Well, we'll post the code. Actually, we should preview it before we do it. And it's not a bad looking toolpath, but we really don't want all these lines to be appearing on our part. So if we move it over and zoom in, we can see that it's actually going to be comping in an arc into the part, coming back around, and coming off the part, wrapping up, going back over, and feeding down that distance and going again. This isn't a bad toolpath, but if we want, we can actually use this pitched arrow. If you hit the what is this, it actually tells you what it is in a dialog box. But I'm going to explain it. Basically, the pitch is how much it's going to go down for every revolution around the part. So if we type in 1/8 of an inch, every time we go 1/8 of an inch down around the outside of the part. So we'll get what looks like a helical finishing pass. If we hit preview, we can see that we have a helix. Get that so we can see it real well. So just like that, we have a helix that comes down. So it comes in and it just helixes down, and it does a pass along the bottom, all the way around the bottom of the pocket. This is a very nice finishing pass and works well in softer materials, harder materials. It's just all around a little bit better. It's kind of fun to watch in comparison to the other one. And another benefit is it only gives you one compensation number that you need to adjust when it goes into the pass. So we're happy with that. We'll post our code. And we're going to do another one around the other circle. We're not changing our cutting data. We're just going to change the center position to 0. We'll preview. If you already knew you were going to be happy with it, we could have just hit post code after we adjusted this. We'll verify the toolpath. So now we have 2 pockets and 2 finish passes. Well, you may look at this and say, wow, that's an awful lot of material that we're going to take away. This is actually the new compensation that's done inside of Mach3, the advanced comp. There's a G-code that is set in the beginning that actually sets your machine to advanced comp whenever you run one of the newfangled wizards. We did this because it's a little bit better compensation routine, and it gives you the opportunity to have a pocket that you can actually tweak the size of it without reposting the program by adjusting a P parameter. This P parameter will be right on the line before it starts cutting this, so it would be like a G41P and the radius of the tool. So as you adjust that radius, you can adjust the diameter of your part. So we have all the milling that we'd like to do, but we'd like to put a couple of circular hole patterns around our part. We're going to change to tool 3. It's going to be a 0.375 or a 3/8 end mill. Tin-coated high-speed steel. It has 2 flutes. We'll calculate it, see what it comes out with for our RPMs. We want to be at 100% and 100%. I'm fairly happy with that. And hit continue. Now we'll start at the 0, 0 position. We're going to do 5 holes with a 3-inch diameter, which is this diameter here. And of course the number of holes is just the number of holes in our pattern. This number could be any number you'd like. 1 is not a valid option, but 2 is. And if you wanted, you could have 1,000 if you wanted to cut the circle out with a drill bit. And the start angle is actually this angle right here from the 0 line where it starts the first hole. This is good if we were to do like a 4-hole pattern and we wanted it to be in a different orientation, so we set it at 45 degrees. We'll preview this. You can see that it's just a square hole pattern if we look at it from the top. But if I go back and take this 45 out of it and put in 0, you can preview the toolpath. And now it looks like a diamond. so we can control the rotation of it. So this would be good if you had a bearing housing or something like that that you wanted to try and get in the right orientation. For us, we're going to put a 5-hole pattern, and we'll start it at 0 degrees for this hole. And if you notice, this value right here is negative. In many of the newfangled stuff, a negative value or a positive value for stuff like a hole depth, both of them are just as valid as the other. We did this because you could see how a depth could be assigned as negative or positive, because it's kind of like, yes, I want to move an inch down from here. So it could be negative, or you could say, yes, the depth is 1 inch of... So if you'd like, you can type a positive or a negative value. I'm going to put in 0.75. And we can select our drilling cycle. We'll do... Actually, let's pre-drill the holes with a spot drill first. So we're just going to go 0.1 in depth with a straight drilling cycle with a rapid height of 0.125 and 0.25. But if you remember, we set our tool data up incorrectly. So we're just going to cancel, go back to the beginning, adjust our tool number. Our spot drill is actually tool number 1, and it's only about 100 thousandths where it's going to be cutting at. When I hit my post code, I can see that, calculate speeds and feeds, I can see that the RPM was just gone right up through the roof. So I'd like to back this way down to maybe 50%, but I really don't want to adjust these values. So I could actually type in that I only want 1,000 RPM, and I would only like to feed at 3 inches per minute. Now let's hit continue. All the data that we had set last time is all set. We have our depth. We hit preview. We can see we just have a small depth of cut. We'll post the code. We can verify and see that, yes, we have a tool path around the circle at 0. We'll put another one over here around at 6 inch. Continue. And we'll enter a 6. And we'll post the code. Verify, and as you can see, we've got the 2 hole patterns drilled out. Now we want to drill them actually to depth, but before that, let's put a hole pattern around the outside of this as well. We're going to keep the same tool to pre-drill, and the center position is going to be 3 inches over. This actually needs a little bit of an explanation, because the set position button, this bounces the the LED, around the inside of the part. What this LED represents is where this 0, 0 is relative to the hole pattern that it's going to program. So right now, if this was at 0, 0, this would be right at our home or fixture offset position on the part. Since we have a hole at 0 and at 6 inches, we're going to set ours at 3 inches to put this pattern right in the center of the 2. But sometimes you may want to start at one of the holes and work your way around. So now we have a width of 4 inches, which our width is here, coming towards us. We're going to run 3 holes in that pattern. So it would be 1, 2, and 3. And 6 holes along the length with a 12-inch length. And if we hit preview, we can see that hole pattern. If we hit the grid button, you can see that it added a row right here. Well, I'm going to show you that if I was actually to put this at 6, so it was a 6 by 6 pattern, and hit preview, it's just going to turn our part into Swiss cheese. This is good if you're going to make something that needs to drain, or if you need to lighten up some stock because it's too heavy, or a number of reasons. I'll turn that grid off and preview it. And that is the correct pattern that we'd like to have. The depth of the hole we need to bring back to 0.1. And our drilling cycle to a G81 cycle, because we're still running our center drill. We'll preview the pattern. It looks good. Post the code. When we verify our toolpath, we can see that we've now put a hole pattern around the outside of the pockets with a whole circular pattern with a rectangular pattern. Go back, and now we want to drill our holes all the way through. And we're going to go in here, go back to tool 3, because that's the one that's got our 375 drill in it. tin-coated high-speed steel, calculate, continue. We're going to adjust our depth to 0.75, and we want to do a deep hole cycle with a 1/4 inch peck. When we preview this, looks good. We'll post the code, we can verify, and now we want to drill these ones a little bit deeper. Continue with the same tool. We're at the right point on the pattern. Bring this to 0.75, and our peck distance, change our drill cycle. We can preview. That is what we want. Post our code, and we'll do the same thing with the hole pattern at 0, 0. Post code, verify. Now we actually have a fairly complicated part that actually didn't take us all that long to program. Found this very handy in the shop when someone needs something fairly quick, to just put a hole pattern in something or pocket out a pocket and any number of things like that. The linear hole pattern and multiple hole pattern are very similar. The linear one actually allows you to put a line of linear holes, but in any angular rotation around a point, which is kind of handy in times. And this multiple hole pattern actually makes it so that we could put holes anywhere, up to 20 different positions. As you can see, 11 through 20 and 1 through 10. So if I was actually to program in positions for a hole pattern, here I would turn on the position and I could move back and forth through the wizard set to actually type in all my data, turn all of the hole pattern stuff on, set my drill cycle to a G81, put a small depth, post the code, come back in, turn off the holes that were the wrong size hole for the drilling operation we're going to do, change my cycle, change the depth, post the code, and go back through. And I can actually do about 5 different size drills with the same thing by only typing the data in once, which seems fairly handy and works quite well out in the shop. That didn't make a whole lot of sense to you. It probably will once you get to use it, just because it's a little more intuitive than me talking about it, and I'll probably do a Wizards video on that as well. But I just want to kind of give you a tour through the package and explain what some of the stuff is actually meant for after you've seen how it kind of functions. This one's very similar to cutting a circle. Mostly all the same parameters, where you have a sweep angle and a start angle. The sweep angle is incremental from where the start angle ends. So if we were to put this at 45 degrees, we'll start at 45 degrees and we'll sweep 180. Just like that. So we started here and swept this way. If we type in negative values, this is one of the instances where a negative value will change the effect of it. You can see that it goes the other way. Same with the start angle. If you type a negative 45, you'll end up coming out the other way. So some of the things, negatives will matter, but it's fairly intuitive on where you'll have a problem with positive versus negative. Cut keyway. This is a typical shop application. Probably the best thing to do would be to call it cut slot. This one actually has ramp angles and stuff like that. If you preview the toolpath, we can see from the side that it's going to come down and ramp to the depth, continue to the end of the slot, pick up, go back, cut out the ramp that it had put in, put another ramp in, and carry on till it gets to the bottom of the part. When it gets to the bottom of the part, it's going to do an offset pass all the way around to clean the slot out to the right width, because of the tool that we had selected was actually not wide enough to cut the slot. This is good for a lighter machine. If you enter a value larger or too large, like if I were to put 200 in here, which is an unrealistic ramp angle, and hit preview, it just does a straight plunge. Many of the options inside the newfangled wizard set, if you type an irrational value into it, it will just go to one extreme and know that you probably didn't mean to type in what you did, but that it will give you something that makes a little more sense. Cancel out of that. We have surface material. Surfacing material with feed stepovers and rapid stepovers. The rapid stepover is seen in red, so it would come down and pick up, go over and wrap it back down. Well, actually, it's a feed move down, and then cut across. This was done for larger diameter shell mills where actually feeding over takes a little bit too much time, and it's more time efficient to just wrap it. Whereas with a small end mill, the feed step over is a little bit safer because you never pick up off the part, and it stays on the part the whole time. This one also uses the start position, just like the whole rectangular hole pattern that we did, so we can set what corner we're relative to. This is kind of handy because sometimes your 0, 0 might be set up over here, so you want to set up the pattern off this corner to cut. It doesn't actually change where the cutter starts. It will always start in this back corner, but it changes where your 0 position can be so that you can program it a little bit easier. Or make it work a little bit better with your other wizards that you're going to be running inside of this set. We'll go cancel out. The next operation we have is thread milling. We hit continue. This one's kind of an advanced milling, but this makes it fairly easy. I'll explain some of the parameters in here. Your center position's fairly self-explanatory. Your thread major and minor diameter are something that you'll have to look up inside a book. The major diameter is quite easy. The major diameter is going to be pretty much the outside of the stock. So if the major diameter is what you're cutting to on an internal thread, it's just the outside diameter of the thread, which is normally called out. If you had a 1/13 bolt or something like that, it would be a 1/2 inch. But the minor diameter is something that's usually not as well published, and you'll have to go to something like the Machinery's Handbook or another resource to try and find that. Threads per inch. In inch, it will actually do TPI, which is threads per inch. In metric, it will actually do this in pitch. So if you're cutting in a thread per inch kind of a thread, you would have 10 threads per inch. So you can just type 10 in here instead of trying to get out your calculator and figure out what the pitch would be. I did that to try and help myself out, just so I didn't have to remember many numbers and just look at the print and just type it in. Your rapid height is how far it will stay above the part when it comes in, and the depth, of course, is the depth that it will go to while it's cutting. We have the choice of an outside or an inside thread, a left-hand, right-hand thread. We also can do a multiple pitch cutter. This multiple pitch cutter is a lot different than the one you see in the picture here. It actually would look more like a tab, except it's actually an end mill with a series of threads up the side of it. So it would go around this stud sticking up in one pass and actually cut all of these threads. This is used in a more high production application and is also a dedicated tool for every pitch of thread that you'd like to cut with that tool. This one was actually modeled after one from a company called Micro 100. It's a fairly expensive little end mill. It's about $45, but you can cut every pitch that you'd like to cut with it. You could even cut a pitch large enough so you could thread a backplate for a chuck on a lathe. If you had a threaded spindle, you can do an enormous thread, all the way up to probably a 4 pitch or greater even, I think. And we also have the option to climb mill or conventional mill. So hopefully that shows you what most of these parameters are in this wizard. And then we get down here to where we have the rectangular pocket. The rectangular pocket's a little bit different because it actually has the finish amount and finish feed rate right inside of this. This finish feed rate, it's probably ought to be a % of what you would like to have it in the other one, and that could be changed. We have our set position, which is just like the rectangular hole pattern that we did. We have step over percentage, the length and the width, similar to what we've done before. We have a direction for the roughing, and we have a direction for the finish pass, as well as rapid height, step depth, and regular depth. In the future, we'll be adding ramping to this, as well as maybe cleaning up this finish stuff a little bit, so it's a little more intuitive for what you're doing. Hit cancel. And the last two that we haven't really gone over is the cut gear and cut spline. I'm not actually going to get into these too much as they're a 4th axis application, but what I will mention is that this one actually feeds the tool from the top, whereas the gear feeds it from the side. So your down feed in this is actually in the z-axis, or I should say in-feed, and the in-feed in this one is in the y-axis and cuts along the x.
So if you have a side cutter like this gear cutter here, it would actually work out fairly well, because you could just put it in and have it go around and cut all these gears out. I've actually cut a few gears with this wizard for various projects, and it seemed to be quite helpful. You have to thank John Stevens for coming up with the idea of that. That pretty much is all of the wizards that are inside the set at this point, and there's new ones being added all the time. When we hit exit, we're brought right back to Mach 3. In Mach 3, you'll see that our program is called up, our toolpath is loaded, and we're ready to cut our part. But if you'll notice that our program was posted for soft steel, so the wizard has actually put notes inside the program to help us through the code. If we hit Edit G-Code, we can see that we have a safe startup block, we're an inch, and we have our tool setting information. This is put in every time you make a tool change, or you change the tool data inside the tool selection page. And if we scroll down, we'll see that we have our next circular pocket, but we don't have any tool data. This is because we didn't select any new tool data. Whereas if we go to the next section on our groove, where we were cleaning out the pass, we did change our spindle RPM, which is why we now have that. We keep going down, and we get into our patterns, and we change to a drill bit. And this drill bit, actually, we set it back to tool 1. This was for our spot drill. Then we get down here, we change it again for tool 3 for drilling with our 375 drill, and then we get to the bottom where it stopped our program. But you'll notice that nothing else was put here. After we got done programming, we actually went through the wizard set and moved around a fair bit, but since we hit cancel, nothing else was appended onto the file. Well, hopefully that gives you a little bit of an explanation on how the wizard set works and what you could do with it. If you have any questions, feel free to email me or put it on the forum. Thank you very much.